Like light, sound is also a form of energy, but it travels much more slowly than light. That is why events can be seen first and heard later. During a storm, we see the lightning first and then hear the thunder.
Sound always needs something to move through. We can show this if we put the clock inside this special jar. At first, the ringing becomes quieter because the clock is now inside the jar. The air inside the jar can be pumped out. The gauge shows that with each pump, more and more air is being removed. Most of the air has now been pumped out. The bell is still ringing, but we can't hear it. As the air is allowed back in, the bell can be heard once again. This shows that sound vibrations need something to travel through. Here, it's air.
So, another difference is that because light is a form of radiation, it can travel through space, a vacuum. But sound can't. It travels as vibrations of the particles of a medium. And this medium can be a solid, liquid or gas. But exactly how does sound travel?
As I pull the bow across the string, the bow makes the string vibrate backwards and forwards very quickly. By using a strobe light, we can see the individual vibrations more clearly. All musical instruments need something to vibrate to make the sound. This loud sound is caused by my lips vibrating.
So you should know for your test that light travels much faster than sound, approximately 1 million times faster. Light is also a form of radiation and can travel through a vacuum, whereas sound travels through a medium as vibrating particles and cannot travel through a vacuum. When we talk about sound, we're actually talking about waves. Vibrating objects, such as my vocal cords, set the air around them vibrating. The particles of air vibrate, creating the waves that transmit the sound.
Imagine you could see what's happening to the air as I hit the skin of the drum. The air is made up of many tiny particles that surround the drum skin. When I hit the drum, the air particles next to the drum skin vibrate and collide with each other. In slow motion, you can see the vibration pass along the line of air particles. It's called a compression wave because the particles are compressed together.
In the next clip, write down the names of the different materials you see sound travelling through. Why not jot down the different materials as we go through them?
Where is that noise coming from? How can I concentrate with all that?
There's someone out here who knows a lot about sound. Dr. Vasudevan. Maybe she can help.
Right, that's fine, let's take a break. That was very beautiful, but it doesn't exactly help me concentrate. I'm trying to find out what medium sound travels through, but all I can hear is their music.
You were sitting in a concrete room with a closed solid wooden door.
That's right, and I can hear myself think.
Well, there. Two more materials the sound can travel through.
Wood and solid concrete. I never thought about that. How does sound do that? Travel through a solid concrete wall?
Let me show you something.
A music box?
Go to that corner of the hall. You'll find some equipment I've left over there for an experiment.
There's no scientific equipment over here, just a tin and string.
That's it. Can you hear the music box?
No, no chance.
Now put the tin to your ear.
No problem. Just like a string telephone.
Exactly the same. You see, not only does sound travel through solids, it actually travels through some solid objects better than it does through air.
What are the girls actually doing?
They're synchronized swimmers, rehearsing for an underwater routine.
Underwater? They're going to have a bit of a problem hearing the music underwater, aren't they?
Do you think so?
So sound should have no problem travelling through water. Let's see. I have a specially designed microphone that can go safely underwater. It's wired up to a speaker so we can hear what the microphone's picking up. OK, Latta?
Above the water, I can't hear the submarine's motors at all. But underwater, what happens? Will the microphone be able to pick up the sound? No problem.
So with their waterproof speaker, the girls don't have any problem hearing their music after all.
The question again. Write down the names of the different materials you can see sound travelling through. So, how did you get on? There were 5 different types of materials that sound travelled through. Wood, solid concrete, string, air and water. Sounds vary in 2 important ways. They can vary in loudness. That's the amplitude. And they can vary in pitch, either higher or lower. That is their frequency. Let's look at amplitude first.
Wow.
Was that the sound that was causing the paper to move like that?
Yes, it was, but I had to make a very loud sound to make it happen.
But what actually makes sounds loud?
Well, you know that sound is caused by things that vibrate, and the bigger the vibration, the louder the sound.
When I hit this drum gently, the vibration is very small. The polystyrene balls only just move, and the sound is quiet. The loudness of a sound depends on the size of the vibrations that made it. The size of a vibration is called its amplitude. The bigger the amplitude, the louder the sound.
So, how loud or soft a sound is dependent on its amplitude. Now that other property of sound, its frequency.
When you tap this glass, it makes a sound as it vibrates. This piece of equipment counts how many times a second the glass is vibrating. The rate at which something vibrates is called its frequency. Frequency is measured in hertz. This glass is vibrating 400 times a second, so the sound has a frequency of 400 hertz.
So frequency is the number of vibrations a sound produces in 1 second, and the frequency will affect how high or low the sound is. That is its pitch. Let's have another listen.
I've got my own frequency generator here. Now, when I shorten the length of the overhanging ruler, the frequency of vibrations increases, and you can hear the sound change. It goes up in pitch. Listen.
The only way we can see sound waves is to use an oscilloscope. A microphone can be connected to an oscilloscope so that when a sound is made, a trace is seen on a screen. The amplitude is the distance from the central position to the top or bottom of the wave. The wavelength is the length of each complete wave, and the frequency is the number of vibrations each second. So this trace has more waves in a second, therefore a higher frequency, a higher pitch. On the other hand, if the amplitude of the wave increases, the pattern of waves gets bigger, demonstrating a louder sound. So, for your test, you need to know that amplitude is the greatest distance that a vibrating particle moves from its rest position, and frequency is the number of vibrations each second. We hear sounds because the vibrations in the air cause our eardrums to vibrate. These vibrations pass from the eardrum through 3 small bones called the ossicles to the inner ear.
The range of human hearing is exceeded in nature by many animals, but our hearing sensitivity is remarkable. A good ear can discriminate between some 1,600 different frequencies.
Humans can hear sounds that have frequencies from about 20 Hertz to about 20,000 Hertz, but not everybody can hear the entire range. Exposure to loud sounds causes hearing loss partly through excessive wear of the ossicles. A very loud sound can cause permanent damage to the eardrum or the ossicles. So, you should know that we can hear because sound makes our eardrums vibrate. And this sound is within the frequency range of 20 to 20,000 Hertz. But as we get older, the eardrum becomes floppy, so the range of sounds we hear decreases, and very loud sounds can damage the eardrum, sometimes permanently. Well done! You have finished both light and sound. Now, if you're not sure of any